So let's talk about Betelgeuse or Betelgeuse, the giant star in Orion. Here's a picture that I took of the constellation of Orion, perhaps my favorite constellation of all. And you can see Betelgeuse glowing red at the top there. You've got the blue stars of Rigel at the bottom and Orion's belt and the other two corners. And you can also see the Orion Nebula there. So quite a nice little photograph. So Betelgeuse, it's a red supergiant star, and I use the term supergiant very precisely here. The temperature, a bit cooler than the sun, 3,800 on the outer photosphere, the surface of the star, giving it that cherry red color. The sun is 2,000 degrees hotter and a yellowy white star. Now, when we get into the other facts about Betelgeuse, we find that there's a little bit of variability here in terms of our state of knowledge. The estimates of the mass, if you go look it up, you'll find that it's anything from 14 to 19 times the sun's mass. That's a difference of 5, which is sort of, well, about a third of the mass, really. So that's a big difference. And based on that difference in mass, we also don't know the power output, the true luminosity. It could be anything from 67 to 87 times as much heat and light coming out of the star. We also don't know very well how fast it rotates, somewhere between 30 and 40 years for it to spin on its axis. That's quite a big change. Now, one of the problems is it does vary. It is a slightly variable star, changing from being magnitude 0, very bright indeed, dimming down to about magnitude 2. And that's about a factor of 6 difference in the actual apparent brightness. So it's classified as Alpha Orionis, the brightest star in the constellation of Orion, but most of the time Rigel actually outshines it. But then in 2019, what really attracted everybody's attention was that it suddenly started dropping its magnitude, getting much dimmer. And we'll talk about that in the presentation as we go through. So here's Betelgeuse, top left-hand corner star of Orion there, and it is massive. This is an actual image of the star, and you can see that it is nearly the size of Jupiter's orbit by comparison with the little diagram that we have there. If we compare it with other stars, then it's truly huge, way bigger than Antares, Rigel, Aldebaran, something between 650 and 750 times the diameter of our sun, a real monster. So large that if you put it where the sun is, the sun would be right in the center of the solar system, and the Earth's orbit would be long gone. It would be way out, and its outer reaches would be, in fact, partly going through the asteroid belt, maybe even out as far as Jupiter. Truly enormous. So it's a good job that we don't have a star like that in the middle of our solar system, because the Earth would be toast. Now, it's also hurtling across space. It seems to be moving very rapidly indeed, traveling across about 30 kilometers per second away from its point of origin, which appears to be the star cluster, the Orion OB1 association, which includes all those bright stars of Orion's belt, Alnitak, Alnilam, Mintaka. Those are all blue, hot, young, bright stars. But Betelgeuse seems to be ejected from that cluster and hurtling across space. Here's a better image of the star itself. It's one of the few stars that's large enough that we can directly image it. And it shows some slight irregularities. We've detected evidence of huge star spots on the surface, cooler regions, large convection cells. But we also see an atmosphere around the star, and that lump on the side there is a bit of brightening in the atmosphere. So quite irregular, and not too much of a surprise, because these very large stars, these supergiants, are holding on to their outer layers at that great distance from the center of mass relatively weakly. Now, when we say supergiant, we really mean these stars right in that top grouping in the Hertzsprung-Russell diagram. You can see Betelgeuse is the extreme top right-hand corner there. The cool outer layers giving it the red color, but a mass somewhere up in the very, very top region where the most massive stars exist. Now, such stars are actually pretty rare. Nature has a much easier time getting the material together to make small stars than it does big ones. You have to collapse the material and keep on collapsing it. But once it gets dense enough in the center to trigger nuclear fusion, the heat created switches on the star and the radiation pushes away any more infalling material. So unless you can collapse a lot of material very, very rapidly, you don't really end up with a large star. It will self-limit. So we get a lot of the small stars and only a very few of these really massive stars. We also observe few, not only because they're rare, but because they don't hang around for long. They live rather short lives. We'll see more about that as we go through the presentation. So even if they were formed, they're not there for long enough for us just taking our snapshot view of the solar environment and the stars in our galaxy to really see very many. But the definition of a supergiant isn't just an even larger star than a giant. It's actually rather technical, and it relates to the spectrum of the star. We spread the light out into its component colors, and that's been done for Betelgeuse here. And we're looking in the top rows at some of the infrared bands there. But you can see the dark lines carving across the spectrum where absorption is being carried out by material in the outer regions of the star. And the crucial fact with supergiants is that these bands, these lines in the spectrum, are really quite narrow. There are an awful lot of them, and they're very narrow. This gives us a great chance to be able to identify them accurately and work out what the elements and molecules in the star and the star's atmosphere really are made of. And it's because the surface gravity at the edge of these huge stars is really very weak. So the churning processes and the difference in the movement of the molecules in the bands is quite low. So you're not getting quite as much spread from the Doppler shift as the material is churning around, because it's in a relatively weak gravity environment. So it's not falling as fast as it would otherwise be. And so it goes with the territory. A supergiant star, regardless of its mass really, just because of its sheer size, has weak gravity at the surface and therefore very sharp bands. Now, in terms of pinning down some of these physical characteristics of Betelgeuse, one of the things we might like to know is how old it is. And again, the estimates of that are somewhere between 8 and 14 million years. Not only is that quite young in cosmic terms, 14 million years is not very much at all, but there's quite a wide margin there. You can see it's 8, or 8 plus 6 is 14. So there's a margin of sort of plus or minus 3 from the middle point there out of only a dozen or so million years. And that's 25% error. So it's another of these characteristics that we do not know very accurately. And the principal cause of our problems is trying to pin down the distance. When we measure distance to the stars, the first step that we really carry out, it uses parallax. That was done with looking at the planet Venus passing in front of our sun to establish the Earth-Sun distance. And then from there, we can use the size of the Earth's orbit as a baseline and look at the apparent change in position over a 6-month period of nearby stars against the background of extremely distant ones. And we can pin down the distance to those. And that was done in the 1800s to begin with, and with gradually increasing precision as instrumentation got better. And estimates in the early 1920s, about 100 years ago, were that Betelgeuse was 180 light years away. But in the intervening 100 years, many different attempts have been made to measure it, and it's varied anything from that figure of a relatively close by 180 years all the way up to 1,300 light years. So a big, well, nearly a factor of 10 variation in the estimates. Of course, a lot of these measurements being done from the ground, but we did have, back in the late 1990s, a satellite called Hipparcos, which had a single job, which was to measure the distance using parallax, using the fact that it was in orbit above the interfering effects of the Earth's atmosphere. And that gave us a distance to Betelgeuse of 427 light years. Now, with that distance and the perceived measured brightness that we see, we can estimate how much power the star is actually putting out. It's so-called absolute magnitude. And from that power output, we can infer how massive it must be. And if you do that, you get a mass of just 7.6 times the mass of our sun. So that crucial figure, 7.6. Now, later on, the data from Hipparcos, 10 years on, was re-evaluated, and they bumped it up to 500 light years, making it a little bit more massive. It's further away, then it must be inherently more powerful to be seen as brightly as it is. So the larger the distance estimate, the more massive we tend to conclude the star must be. Moving into this century, in 2008, the radio telescopes of the VLA out there in the desert were able to have a go at this, and they got a distance that was 643 light years, so a huge uptick in distance. And again, further away means more powerful and more massive, so we're estimating it up to nearly 20 times the mass of the sun, an estimate of around 19. Bringing it more up to date, in 2022, physical astrophysics modeling of the star, comparing what we see in terms of the elemental composition, the size, and the other parameters that we can measure from the spectrum, give us a much lower number, 410. So that's a much less massive star indeed. And it really makes an enormous difference to us. Now, you might well ask, what about the Gaia mission? What about the Gaia spacecraft out there orbiting in space at the second Lagrange point, 1 million miles from Earth? It's supposed to be mapping 1 billion stars, and naturally that would include the star Betelgeuse. Well, there are really some issues to do with actually trying to use this, because of the nature of Betelgeuse, which I'll say more about. But Gaia has been unable to come up with an accurate answer. So we're still really rather guessing the distance, and therefore the power output, and therefore the mass. Which leaves us with one really big question. Will it go bang as a supernova? This is a picture of the Crab Nebula, another supernova that blew up 1,000 years ago, where a giant star had reached the end of its life. And we talk about the evolution of stars. We often show this diagram. We show them forming from a cloud of gas and dust, and then taking one of a couple of different paths. For small stars, they go along the top trajectory. They live a nice long life, converting hydrogen to helium as a main sequence star, a normal star. As that helium builds up in the core and the hydrogen ceases to fuse in the center, starts burning in a shell around the core, which is inert, they swell up to red giants and then puff off their outer layers to form a planetary nebula. Sometimes that's triggered when the degenerate core in the center of the star suddenly fuses all the helium to carbon. in a very short period of time called a helium flash, which is another whole topic that we might cover one day. And that sudden release of energy can be responsible for pushing the burst of material away from the center of the star, giving these multiple shells of ejection that you see here in this picture of a planetary nebula. But the point is, it then goes away, dissipates into space, leaving just a white dwarf, often made of helium and carbon and oxygen right in the center. And whether or not it goes on to form carbon and oxygen depends a little bit on the mass. But this top track, that's for stars below a crucial value of around 8 solar masses. It does vary a little bit depending on the chemical makeup of them. So for larger stars, they take the bottom route. They become giants very quickly. They burn through their hydrogen. They form supergiant stars, and they are able to go through a number of phases, burning up by further stages of nuclear fusion until eventually they run out of options and explode as a supernova. And then one of two things can happen. For the stars in the range 8 to 20 solar masses, you will probably form a neutron star. If it's more than 20 solar masses, then the theory goes that it will collapse down immediately to a black hole. But things are a little bit more complicated in terms of the evolutionary stages, and I just wanted to cover this bit. After you leave the main sequence, and we're showing the trajectory on the right here that you would take across that famous Hertzsprung-Russell diagram for a few different masses of stars. So if we look at the sun there in the middle of the diagram, it will convert hydrogen to helium for a very long period of time and then swell up into a giant star. The outer layers expand and cool, and that is because of the helium build-up in the center, killing nuclear fusion in the center, making the star less efficient. It's only able to fuse in a larger shell around it. The larger shell has a greater surface area, so the heat radiation from that fusing shell is greater, in fact, and it's able to push the outer layers outwards. And it takes that trajectory up where it says RGB, red giant star. And if it's hot enough, if it's powerful enough, it will form this ball of helium in the center that becomes a degenerate ball of matter held up by, rather than just simply by the energy and the fusion, but by electron degeneracy pressure, the quantum mechanical effect. And if that becomes overwhelmed, if there's enough mass there, then suddenly the helium will be fused to carbon and oxygen in a so-called helium flash, and the star will suddenly become much more energetic for a short period of time as it does so, and it will whiz back across the diagram into the yellow region, becoming a yellow giant. Once that then dies down and you start forming an inert carbon-oxygen core, then it will be burning helium in a shell over the top of that and burning hydrogen in a further shell, so starting to build up that sort of onion diagram that we sometimes see, and becomes an AGB, an asymptotic giant branch star, up there to the top right. For a 5 solar mass star, things happen a lot more quickly. You get the hydrogen to helium stage, and then it goes across to being a red, small mass, red supergiant star in the low end there. Then undergoes that yellow loop again. It comes across when the helium starts to burn. It doesn't undergo the helium flash process. It's much more of a continuous kickoff of helium burning, but it becomes more energetic for a while, turns yellow, and then goes back to being red and heads off further up the diagram. And for a 10 solar mass star, again, the same sort of thing happens there with this these turnarounds and these loops as it's going through the phases. And I've drawn the phases of nuclear fusion at the left there. So after you've formed helium, You ram two helium nuclei together, get a beryllium-8 nucleus. That's highly radioactive and will decay back very quickly. But if you are able to hit it with a third helium nucleus, an alpha particle, in time, then you can form carbon. And if you add another one, then you can get oxygen. And that's the start of this building of the heavier elements. I've got a whole video on the rest of the process about how the elements are formed, which talks about the further stages. And so anything less than 8 solar masses will not explode as a supernova. You get this onion-like structure with the helium and hydrogen shells with an inert carbon-oxygen core where it's unable to carry out any more fusion. It takes a lot more pressure and a much higher temperature to kick off the carbon burning process and the rest of the fusion ladder. So eventually you will end up with a white dwarf containing most of that core there and the outer layers puffed off as a planetary nebula. But if you get bigger, if you're above 10 times the mass of the sun, you can go on and start to generate the pressures and temperatures necessary to kick off the further stages, creating elements like neon, silicon, and sulfur. And for a really massive star, then you can go beyond and start turning silicon into iron and creating all the elements up to the iron number 26 in the periodic table, at least all the even numbered ones. You don't get so many of the odd ones. But you run out of options at that point, and so for the largest stars, once that iron core starts to dominate, it's unable to release any more energy and collapses, and you have a supernova explosion. This is a little animation of the Crab Nebula showing the idea that the star has exploded, hurling all of its elements that it's made back out into space. Now, Betelgeuse has been observed very carefully, and in 2019 it did something very peculiar. It started dimming. It's always varied up and down by 1.5 to 2 magnitudes, but it suddenly took an extra large dip, and this got everybody very excited that it was possibly going to explode at any moment. And our models of stellar evolution would suggest that it is coming to the end of its life sometime soon. So the combination of that and the sudden dip in the light curve got everybody thinking, here it's about to go. Now, I've been looking for it every time during the winter season when we can see Orion every Wednesday night doing our public observing evenings, and it's still there. But I do keep checking just in case, because it would be very, very spectacular. It's actually in the safe zone. It's far enough away that although it would be very, very impressive if it blew up, it wouldn't actually be dangerous. You'd have to be closer than 150 light years, and we're pretty sure it's further away than that now. It's at least 400, maybe as far as 600 or even 800. So what was going on? Well, it looks like, and this is a combination image of an optical image in the center and an infrared image around it. It looks like it was in the process of puffing off shells of material, and some of those contain carbon and oxygen and carbon monoxide and methane, all sorts of chemicals. And the clouds of material were able to start blocking some of the light, and that was probably what was causing it to dim down. So perhaps, as it hasn't exploded since 2019, maybe we've got a bit longer to wait. Now, there have been some observations and attempts to try to find out if it has any companions, either secondary stars or planets. And, well, here's the story. 1985, there was some indications from polarization studies and a technique called speckle interferometry, so ground-based observations trying to rapidly capture the dancing image created by all the turbulence and recombine the images to try to see the star in detail. And some of that suggested that there might be a companion star. But as techniques have improved, such observations have been shown to not be followed up, so probably not detected back then in the 1980s. In 2024, however, it does look like there might be another star, either a small star or possibly even a white dwarf star, in an orbit at 8.6 astronomical units from the star. So roughly getting on for the orbit of Saturn, so not actually swallowed up. But some people have suggested that perhaps it's only 6 and that it'll get swallowed up soon. And other reports are that there is a star within a star, and that some of the pulsating and brightening and dimming that we see and the variations in magnitude are because there is or has been recently swallowed into the distended envelope of the main star a smaller star that's still orbiting and still intact. And that's entirely possible because the outer layers of these supergiant stars are basically a red hot vacuum. There's almost nothing there. They're so thin in terms of the density that another star could orbit round inside it for a very long time before it would gradually spiral in. The resistance caused by the thin gas of the outer layers of the star would be so weak it would take a long time for it to swim inwards. Now, if it did have some companions, we could solve our mysteries, because when we look at how things orbit around main bodies, we have Kepler's laws. First of all, the first law that they move in ellipses. Secondly, that they sweep out equal areas in equal times. But more importantly, we can determine that the square of the period is related to the cube of the radius. And in particular, it's related using a mathematical formula based on the mass of the object in the center. It's actually 4 pi squared over a constant times the mass. And so if we can measure the period with which a body is in orbit, then we can immediately deduce how far away the radius is. If we can see it from an image, and with those two numbers, the period and the distance, we can calculate the mass. So we would be able to figure out exactly how massive Betelgeuse is. That would then be able to work backwards to working out the distance. So it would solve all of our problems that compound from the fact that we don't know either of those two variables. But if we look back at ancient reports, then we find a real mystery. And I came across this in researching the topic. And that is that we see Betelgeuse as a red giant. Ptolemy describes it in Greek there as an orange tawny color. Well, I would probably agree with that. I would say it is a reddy orange, but it's more red than orange at the moment. So maybe there's something interesting there. But more significantly, Chinese reports from 300 years prior report it as yellow. So could it be that just over 2,000 years ago, 2,500 years ago maybe, it was actually in the yellow giant stage, having kicked off helium fusion and now has returned back across the Hertzsprung-Russell diagram, having passed through what we call the instability strip and settled back down from being in the red giant branch to being in the asymptotic giant, the AGB era. Well, that would be interesting if that were true. If we could rely on that, it might tell us that the mass is smaller than we think. And again, that it was likely to die as a planetary nebula. The other thing about knowing the mass is it would tell us when. It would tell us when the star will come to the end of its life. There's a formula. The lifetime, tau, is 10 to the 10 years times the ratio of the mass of our sun, m with the little ring after it means the mass of our sun, divided by the mass of your chosen star to the power 2.5. So in fact, if you double the mass of a star, you will reduce its lifetime by what works out to be about a factor of 6. So the sun will live for about 10 billion years. It's about halfway through that at the moment. But bigger stars, they will live fast and die young. They burn their fuel at a prodigious rate. Even though they have more of it, they don't last as long. And a star that was 10 times the mass of the sun, if you plug that into the formula, you find that it's 300 times less long-lived. And so that 10 billion years comes down to just 33 million, really quite short. But if it was 20 times, the factor is 1800 to 1, and it drops to 5 million. And that's the real point here, that if Betelgeuse is 20 times the mass of the sun, it's only going to live for 5 million years, and it's likely to blow up tomorrow, or indeed already have blown up, and the image of it having done so has not quite reached us yet, because of course it's several hundred light years away. So if you take that view, you might say that it might already have exploded, and the light showing that hasn't got here yet. It really could be at that end of things. Whereas if the estimate of the mass is half that, at 10 times the mass of the sun, it would still explode as a supernova, but you might have many millions of years yet to wait. So fascinating to find out. And as I say, we either need to find the distance accurately or find the mass accurately. Either one of those will solve our problem. But the only other choice is to watch and wait. So thanks very much for listening. I hope you've enjoyed that trip once around Betelgeuse there, the bright star in the corner of Orion. And I'll bring the recording to a halt. Thanks a lot for listening.